of research in Silicon Valley. He graduated from MIT in 2009, where he did his PhD with Indyk. And his research interests are in high-dimensional computational geometry, basic embedding, sublinear algorithms, streaming algorithms for massive data sets, and theoretical machine learning. And today he's going to talk about sublinear algorithms via physics.
Thank you for the introduction. Can you hear me all right? Okay, so first of all, let me say kind of a couple words about my background. So I'm kind of more in theory community, and you know, this talk is a bit more technical than perhaps some of the talks from previous days. So the main thrust is, you know, really talking about essentially a sampling technique. You know, like it's a specific question, before going there, you know, I'll just tell you kind of, you know, a couple slides about what I mean by sublinear algorithms, right? And this is essentially a topic of interest in the theory community, you know, which addresses some of the challenges for massive data sets. And let me mention that these slides are based on some work with Robert Campino from Weizmann Institute and with Krzysztof Wanak from CMU. Okay, so sublinear algorithms, this is just, you know, like really kind of very high level kind of toy slides. So algorithms, you know, usually we're thinking that, you know, what you have some data, you have some resources, a computer, you want to solve some problem for this data. You know, you go to the textbook algorithms, you get an algorithm, and you know, you implement and solve it. And you know, we were happy when the algorithms are fast, and generally our kind of gold standard was, you know, linear time, which means that, you know, you use time and space which is roughly proportional to intercept. Now, you know, of course, you know, everybody knows that, you know, data looks like this, and so in this case, you know, at least one way kind of to view this or to model how to approach such problems, such situations, is to think when computer resources are much less than the amount of data, and this leads to, you know, studying sublinear algorithms where we access data in a limited way. In particular, you know, we think, at least there are two ways to think about this. One is limited space, where your, say, main memory is much less than hard drive. And I'll show you a scenario of this on the next slide. Another is limited time, where the time that you are required to spend on this is much less than the time to read the entire data. So more or less you have to subsample. So this is, you know, this is related to streaming algorithms and property testing algorithms that have been studied for many years in the community. So, you know, there's kind of nothing really new, but I just want to put in perspective. So here, let me give you a sublinear scenario, which is more related to this talk. So this is a router, and imagine you have packets passing through. You know, there are many of them, so these are just, you know, IP addresses, and suppose you know, the router wants to store some statistics on this, right? So you have, say, the traffic that passed through. This is, you know, the kind of the histogram of the traffic that passed through. Usually, of course, this table looks like very large, and of course, you know, this doesn't really fit on the router to store it. So the challenge here is really to compute something of this table, some statistics, using small space. So we really want this to implement this, right? Now, you know, such compressing doesn't work. I mean, So you need to do something better here. You cannot just store a table, but let me give you some examples of what is this something. Imagine you want to compute the number of distinct IPs, different, say, connections that are established, say, the moments of these frequencies they have for, detecting some intrusion to do some intrusion detection attacks, or, general statistics on the other. So this is kind of the setting. And where does it come from? Like, well, let me kind of give you a couple more scenarios. Well, one we just saw, this is data passing through the router in the previous slide. Another one you can, where this notion of what is called streaming algorithm, where it appears is when, say, your data is stored on a hard drive. And you think of your say processor and memory being much less than the hard drive, and what you can do, you can stream data from the hard drive, in practice it turns out that it is much more efficient to do just linear scan over the data rather than doing random access. So you can model this as essentially streaming your data from hard drive through the processor or through the network. Okay, so this is the setting. Naturally, there are many applications, say network logs, sensor data, real-time data, actual routers on the network. So this is kind of the motivation. Now, what I want to talk here is essentially a particular construct. I mean, it's intended to be a theorem or a lemma, but I want to talk about that turns out to simplify or give some algorithms in this setting, right? And so now we are switching a bit gears, and I'm, becoming slightly technical at this moment. And what I want to talk about is a particular primitive that I will show later how it is useful for this type of algorithms. And this is very related to sampling, right? The sampling as you know it more or less. So, a common primitive that often appears is you want to estimate a sum. So think of this as we have n quantities, say 1 up to an, in the range between 0 and 1, representing, say, how much traffic passed through, this is the picture. So you have different, say, computers having some different aspects of the data. So the data, say, is partition. We have different aspects of the data, and say A1 is statistics on this data, A2 is statistics on this data, and suppose you have to sum, right? So, you can model many scenarios this way, as we'll show later. But the main point is that you want, there is some monitor that wants to estimate the sum. And this is, the setting where I'm thinking about it. And, this is the problem, right? And we want to estimate cheaply, not using too many resources, right? So what is one way to do it? Well, one very common way to do it is, well, let's just subsample, right? So, say you don't require that everybody sends you your numbers. You say you want to minimize the communication, or you don't want everybody to go and compute their actual number, say 1 after n. So I say that, well, just a subset will send me their numbers, and I'll use the subset to compute the sum. And this is kind of the first sampling thing to do. You subsample a number, and say n out of n, and this is a normalization constant, that would be your estimator. And when you apply, say, standard bound, say, Chebyshev bound, we'll say that with, say, 90% success probability, your estimator, this S tilde, will be, say, factor 2 approximator plus minus some term, which is roughly, some constant times n divided by n. Okay, so if if your sum is, if it is a still that you expect to be roughly proportional to the max value, which is roughly n, but you don't expect to sample many of them, it's sufficient to sample a few. On the other hand, if you really strive for a very small error, think of this as, say, additive constant. For additive constant error, you want this term to be roughly constant, then you really need to sample almost everybody. Right? If everybody has a number between 0 and 1, right, and you want your error up to plus minus 10, for example, then this can be hidden in just a few of these machines. So you need to sample everyone. And so this is roughly where precision sampling comes. So it's the same problem, but we're switching the framing. So this is the slide where something new appears now. Okay, so we think about this as accessing this AI is slightly different. So it is, think of this as a kind of new model of sampling. So again, we have the same setting where we have this number of computers saying this, containing these numbers A1 and AN. And the monitor again wants to estimate the sum. Now what it does, rather than just getting a subsample of them, it will want an estimate for each of them, but for different precisions. So it picks some numbers U1 up to UN, and it tells the computer, tell me this number A1 up to precision U1. So U1 is some number, say 0.01. So tell me this number up to this precision. And what it means to up to this precision, it means that say absolute difference is upper bounded by this precision. Okay? So it says this number says, well, tell me up to this precision, and these guys send back this estimator, and then it uses these estimators for each of the numbers to compute the entire sum. Okay? And the challenge here is, of course, it should be a trade-off between something, right? So on the one hand, we want to achieve as good as approximation to S. Basically, we want this S tilde to be as close to the real sum. One, and two, you don't want to require too much out of each computer. I mean, a trivial solution would be to go to each one and say, give me, putting all UIs to be equal to 0, and saying that give me precisely that number. Right? So, I mean, we didn't get far. So the trick here is to say that, well, we want to get a good estimate, but by requiring, very coarse precision. Because think of this, the model being, or motivation being that it requires resources for this computer to compute this number A1. And the coarser the precision, the less resources it requires, say time. Okay? So this is really kind of the setting. So let me give a formalization of this. Perhaps this will be more clear. I'm actually not sure what. Okay, so formalization is that think of this as essentially a game between two players. One is a sum estimator, the guy who actually wants to compute the sum, the monitor, right? A1 up to sum of A1 up to AN, and the other is a adversary. Think of this as some kind of noise. And what happens is that they fix their things separately. So the sum estimator chooses some precisions. So it's an algorithm to compute these precisions, and adversary chooses these numbers or nature. Then what happens is that the adversary learns the precisions, the required precisions, and spits out these estimators, tildes, that satisfy the precision requirement. And now the sum estimator says that, okay, now I learned the estimators for each number A1 up to A1, and given these things, I compute some S tilde, the sum estimator, such that, say, it is a good approximation, say, up to additive constant error. Okay? Now, I mean, it's clear what, it means to be good in terms of estimating the sum. Now, there is the notion of cost of precision. Right? As I said, we can always set the precision to be equal to 0, and the output will be single, right? Trivial. So what is cost, right? We need to put some notion of cost on our precision, on the required vision precision, and here I'll define. I mean, it's a choice, right? You can imagine different options. I'll fix one. which is the average of 1 over precision. Okay, so if precision is coarse, meaning say it is 0.5, right? Then this number will be relatively small too. However, if I require precision to be very fine, say closer to 0, then it suddenly begins to increase in cost. And there is a particular reason to choose these precisions. I mean, first of all, because it's useful in our applications, and two, you can think of coming back to this motivating example where these AIs are themselves, say, a sum, right? It is these computers which has one particular AI, it has to compute this number AI. And if it is a sum of something else, and if it requires some precision, then this is roughly how many subsamples do you need. If you want to estimate a sum of precision UI, then you roughly need 1 over UI resources, in terms of space or samples or something. So it is natural to measure it this way. So let me give you an example of something with at least bounded cost. Right? So we can choose all precisions to be roughly 1 over n, and the average cost will be roughly proportional to n. And I view it as relatively bad. I mean, we want to achieve better than this. And the thing is that if your estimator, the algorithm to compute the estimator as tilde just sums up the estimates for each AI tilde, then this is the best possible. You cannot go below this cost. So we will want something better, and this is what we show that you can. There is an algorithm, relatively simple algorithm, that manages to go below this number in this frame. So this is just stating the goal succinctly. This is the lemma, which says that again, say with 90% success probability, you get something, say 1.5 multiplicative error, say constant additive error, which probably means this, and the average cost is much less. It's only logarithmic in n. Okay, so in particular, it means that our estimator for tilde doesn't just sum up the estimates for each tilde separately. And let me give you an example why this, in some sense, is even possible. I mean, which may or not be obvious. Non-obvious. So let me give you kind of two extreme examples where things like the entire mass is either 3 or 0. Right? The sum is either 3 or 0. And we want to distinguish between these two cases. And you can think of, depending on how this mass is spread between these AIs, there are two cases, right? Two extreme cases. One extreme case would be where all this mass is really concentrated on some particular computers. So this is the case where the subsampling, they just subsample several of them, would fail. So here, note that essentially it is enough to use a crude approximation follower. So if you choose UIs, which say are 0.1, you are able to distinguish between bad numbers being either 0 or 1. And here it is the case when the mass is uniform. Then here to some degree you can, in some sense, you can use the subsample. Then you just subsample few very good precisions, roughly proportional to 1 over n, and the rest you use with. Okay, this is just to say that you can throw in epsilons here and get say 1 plus epsilon multiplicative error. And here is actually the algorithm. Right? I'll just show you the algorithm how to get this, right? And to say that this is relatively simple. It turns out that there is a reason I chose this variable to call UI. There is so it's enough to choose them uniformly at random between 0 and 1 ID, and then the tilde just counts the number of phi such that that inequality holds. So this is all. Okay, so that this this is roughly the proof. This is proof. This is proof of proof rather than explaining proof of existence. All right. So okay, this is for epsilons. So the rest of the slide will be roughly in the same style, like proof of existence, kind of rather than actually rather than explaining. So why is this useful? It turns out that you can compute norms and moments of frequencies, of these tables on statistics more efficiently. There's one paper, and then in some other work we showed that this technique will help you save some time. In particular, it helped us getting better algorithm for eddy distance. So I think I'm running out of time, so I'll just skip to the end. This is the entire algorithm I did, just to show that it fits in a slide. Some related work, it's not in vacuum, of course. So this is really the conclusion slide. Let me just mention several questions that I find interesting. One is whether some other applications for preserving sampling framework, getting better algorithms, or in general, can we think of other forms of access for these number series to get better estimators? Okay, I guess I'll finish here. Thank you. Question?
Yeah. So initially you stated the goal as finding an estimate S tilde such that S tilde minus S is within a constant, right? But so you do allow a multiplicative factor in the final results. So,
Yes.
So, is it known that a cost better than n is not possible if I want a multiplicative?
Yes. Yes. Perfect question. This is exactly the point that I was a bit lying there. Yes, precisely that guarantee without multiplicative error is not possible to obtain. So you do need some multiplicative error.
If I want 1 plus epsilon, then we know how it behaves as a function of epsilon.
Epsilon to 1 second. I mean, basically.
Other questions?
So how is this related, or have you considered using other measures of the cost, like entropy or information, or if you're sending those in terms of numeric value precision or the bit value of information?
Good question. Yeah. So one can consider different cost models, and using the same model, you can obtain some bounds on them. Why we didn't kind of pursue too much in this direction is that we don't have a concrete application for our cost models. This cost model was useful for the applications that I kind of skipped, but indeed, I think it even mentions here on the slide, right, that it's a very good question to ask about our cost models, but probably it should be kind of connected to some particular applications.
Because this application was routing information sending over the network, that's why I thought
right. It's natural to say, and people suggested this to say logarithmic the number of precision. That's a natural. Yes.
There's no further questions. Let's thank Alexandr again.
Thank you for the introduction. Can you hear me all right? Okay. Okay, so first of all, let me say kind of a couple words about my background. So I'm kind of more in theory community, and this talk is a bit more technical than perhaps some of the talks from.
Some research in Silicon Valley. He graduated from MIT in 2009, where he did his PhD with Indyk. And his research interests are in high-dimensional computational geometry, basic embedding, sublinear algorithms, streaming algorithms for massive datasets, and theoretical machine learning. And today he's going to talk about sublinear algorithms via precision.
Is much less than the time to read the entire data. So more or less you have to subsample. So this is, this is related to streaming algorithms and property testing algorithms that have been studied for many years in the community. So there's kind of nothing really new, but I just want to put in perspective. So here, let me give you a sublinear scenario, which is more related to this talk. So this is a router, and imagine we have packets passing through. There are many routes, so these are just IP addresses, and suppose the router wants to store some statistics on this, right? So you have say the traffic that passed through. This is the kind of the histogram of the traffic that passed through. Usually, of course, this table looks like very large, and of course, this doesn't really fit on the router to store it. So the challenge here is really to compute something of this table. Previous days. So the main task is, really talking about essentially a sampling technique. It's a specific question. But before going there, I'll just tell you kind of a couple slides about what I mean by sublinear algorithms, right? And this is essentially a topic of interest in the theory community, which addresses some of the challenges for massive data sets. And let me mention that these slides are based on some work with Robert Campino from Weizmann Institute and with Krzysztof Łanak from CMU. Okay, so sublinear algorithms, this is just, really kind of very high level kind of toy slides. So algorithms, usually we're thinking that, what we have, you have some data, you have some resources, a computer, you want to solve some problem for this data. You go to the textbook algorithms, you get an algorithm, and you implement and solve it. And we were happy when the algorithms are fast, and generally our kind of golden standard was linear time, which means that you use time and space, which is roughly proportional to input size. Now of course everybody knows that data looks like this, and so in this case at least one way kind of to view this or to model how to approach such problems, such situations, is to think when computer resources are much less than the amount of data, and this leads to studying sublinear algorithms where we access data in a limited way. In particular, we think at least there are two ways to think about this. One is limited space, where your say main memory is much less than hard drive. And I'll show you a scenario of this on the next slide. Another is limited time, where the time that you are required to spend on this is